Okay. Let's start. One things at a time. I work on the most completed channel components. So I start by introducing two form of business. This is James, and there's also a the map is there, and it will talk about a profunctorial semantics for talking Supermaps.
Yeah, so hi, I'm James. I'm a postdoc at this INRIA thing just to the south of Paris. Some work with Matt, who's at UCL in London. So yeah, I'm going to be telling you a bit about profunctors and about supermaps. So let me start by saying, what do I mean when I say a supermap? So usually in quantum theory and in sort of physics more generally, we're thinking about, we've got processes, we've got some systems, they're going to be evolved by these processes through time. So I might have some system A, and evolve this by this process phi to give me A prime. And in particular, this is something that takes some state of this system A and returns me some state of this new system A prime. And there's been a lot of work recently in the quantum foundations literature about kind of trying to take this to the next level, to the higher level. So what do I mean by this? Well, you can imagine now that I've got some process eta, which instead of taking states to states, it takes as its input this channel. So it takes the processes and returns me a new process instead. So it's acting at some sort of higher level of process. And I can take this a stage further by imagining that it's something that actually only acts on part of some tensorially extended process. So it acts just on this part of A here and kind of leaves alone this X part. And this is what I mean by a supermap in a very kind of hand-wavy way. And of course, the point of this presentation is going to be to try and give this a formal meaning. So I've taken some pictures here from a variety of quantum foundations papers. So in the top left here, we've got perhaps the most simple example of one of these supermaps. So we've got some quantum circuit here in this kind of bluey green color. And then they've kind of come along and cut out these holes in red here. And then this overall kind of map that we've got here is now some higher order process. So I could imagine filling these holes with quantum channels. And what I get back now is a quantum channel itself. So this kind of blue thing represents a higher order thing, which takes channels to channels. But the quantum people are particularly interested not in this case, in fact. Okay, this case is kind of the boring one, where we actually have a circuit from an original kind of, from quantum theory, have a quantum circuit. They're interested in these other cases. And these are these abstract other processes that don't factorize into some circuit. So yeah, as I was just saying, we've got these processes here, which we can, if we're thinking more categorically, as some sort of string diagram with holes in them. But then there are other processes that quantum people are interested in, which don't, there's some sort of higher order process, but they don't exhibit a factorization as a circuit. And these might be ones where my holes are ordered in time, or it might be ones where my holes are not ordered in time. So they're somehow sort of in parallel. And particularly this last case is of great interest to lots of people in quantum theory. And there's lots of examples of weird maps that live in this class, the quantum switch, the Lugano process, the OCB process, the Grenoble process. There's lots and lots of these. And quantum people are interested in these because they exhibit all sorts of weird quantum phenomena, exotic phenomena, like superpositions of causal orderings, and they can beat certain communication bands and things like this. So to give you a very brief idea of what one of these processes might look like, you could imagine I've got some quantum system rho, and I have two channels, N1 and N2. And I can imagine passing rho through the channel N1 and then the channel N2. So I go round this path here. Or I could imagine doing it in the other order. So I go around this dotted path and I go through N2 and then through N1. Either of these, perfectly normal, perfectly kind of straightforward classical orderings of the two channels. But I could imagine, now that we're in quantum world, somehow taking a superposition of the two. And now I'm in a situation where it's not clear that N1 is before N2 or that N2 is before N1, and I have some superposition of these two orderings. And in fact, it's known that you can't write this down as a quantum circuit. So there doesn't exist a diagram that looks like anything like something like this. So it really lives as some abstract process like this. And you might say, well, this is completely crazy. What the hell are you on about here? There have been suggestions that ways this could exist in reality to do with taking superpositions of different space-time structures, depending on how you place these masses in the space-time. You can change the causal orderings of these two processes. I'm not going to go into the details of this, but there have been suggestions about how this might occur. So yeah, overall, we've got these sort of simple case networks with holes, but then we've also got these higher order processes that don't really exist in this class. How can we develop some category theory to deal with all of these things? And there are a number of approaches that live in the kind of categorical domain, which I'll give a kind of brief idea of how these work. So the first one is this cause construction. So the idea here is they take a category, a compact closed category C. So I've got like a symmetric monoidal structure. I have an environment structure, which allows me to model causality in this category. And I also have these caps and cups, plus a few other assumptions that I'm going to sweep under the rug. And you turn this into a new category, cause of C. And in here, they can now describe these supermap objects. Essentially, the objects of this new category are kind of richer than the ones of the original category, such that I can deal with various signaling conditions and this sort of thing, which means I don't end up having any time loops and avoid things like the grandfather paradox over here. And this is a very rich categorical structure. It's a star autonomous category. So there's a tensor product, which models the separable processes. And then there's another tensor product given by the star autonomous structure that models all processes. So it's actually a model of linear logic. It's furthermore a model of something called BV logic. So there's a way of kind of sequencing processes, a whole bunch of very rich and nice category theory in here. But in here, there are a number of assumptions, in particular, these caps and cups that we have to have from the very beginning to make this construction work at all. And to give you a vague idea as to why, it's because, well, if I have a process like this, a higher order process, I can use these caps and cups to convert it into something like this. And now I've got a morphism in the original category that I can make sense of. But if I don't have these caps and cups, this is substantially more complicated and this construction doesn't work. And in particular, I won't have these if I'm thinking of infinite dimensional quantum systems, or I'm thinking of various subcategories of quantum systems. So we kind of want to try and move away from having to assume that we have these caps and cups from the very beginning. Another approach is something known as co-end optics. So this is a category where now I in this new category, my objects are pairs of objects from the original category, which kind of modeled the holes. And then the morphisms of this category are given by this rather scary looking equation here. But what you can imagine, or what you can think of really, is that these things are these kind of cone-like shapes, these pairs of maps, quotiented by this sliding relation between the two halves of this cone. This gives you there's a whole bunch of really nice category theory about this that many in the audience here will probably know about, to do with bidirectional data accessors and all the sort of thing that can be modeled in this world. So this is all really nice stuff and can model case one extremely well. So we can deal with all these circuits with holes in them. Fantastic. But where's the cases that the quantum people really care about in here? We can't really talk about the switch or this Lagrange process. So this isn't quite good enough for what we want. And then the third approach I mentioned, which was introduced by my co-author and a couple of other people, is something that they call the locally applicable transformation. And what they did is they went away and they really thought about, well, what are the operational principles, that the axioms, if you like, that I should take for something to be called a supermap. And what they decided upon was essentially this law here. So the idea is if I take my process and I apply my supermap to it, then someone else who distant off in space-time, who has the kind of other half of this process, should be able to manipulate their half kind of freely of my supermap. So that the application of my supermap should commute with their application of this cone-like structure to their half distant in space-time. And they formalize this with this following definition of a locally applicable transformation, which is given by this family of functions together with these couple of laws that it should satisfy. So that the one law says that if this distant party in space-time does some pre and post processing on this morphism, this should commute with the supermap. And if I go and find an additional person way off in space-time, I should be able to kind of tensor this person on, and that should also commute with my supermap. And you can extend this to the case with lots of holes, with the multi-party case in the kind of obvious way. You now have commutation in each one of these holes and pulling this wire into each one of these holes. And what's good about this is, well, this can model the interesting quantum cases. So they demonstrated in their paper that if you now take this definition and apply it to quantum channels, you get back things like the switch to the Garner process, all these interesting things, and exactly those things. Great. And very few underlying assumptions. There's no compact closure. There's none of this in here. But what is this definition really? It's a bit ham-wavy. It's what are we really talking about here? What's the real category theory going on behind this? So it's algebraically rather kind of intractable. Also, what's happened to cases 1 and 2? Can we deal with the supermaps that are kind of ordered in time and those that decompose as codes? And I should say as well that the way that they described these maps in the original paper was as a multi-category. So it's not clear even whether we can turn this into like a proper category and not a multi-category. Are the tensor products there? What's the logical structure of this category? So these are all kind of questions that we wanted to answer to give this a more formal grounding. Okay. So that's what I will talk about the rest of this, is how do we turn these definitions into something more formal, and what do we learn by doing so? So if we go back to one of these locally applicable transformations, it was this family of functions. And the idea is that it takes some morphism phi, which goes from x to a tensor x to a prime tensor x prime, and returns me eta of phi that lives in here. So it's some function between these sets. And I think in this room, it's not too much of a stretch for most people to see that this is a functor into set. Intact is something known as an endo-profunctor. And that then these etas, this family of these etas, are the components of a natural transformation. And if you look then at the naturality square for this natural transformation and unpack this square, well, it's exactly one of the laws that they wrote down. So great. There's one of our laws in nice kind of categorical language. How about the other law, though? Well, to do that, we need to note there's a kind of an additional piece of structure going on here, which is if I take these profunctors that I was interested in here, and I take any other morphism, in fact, these profunctors play well with this tensorial structure. So I can kind of tensor these f's inside any other f inside this profunctor that I have. And this is something known as a strong profunctor. So that's just a profunctor that plays well with the tensor product at the end of the day. And you can then ask, well, what are the strong natural transformations between strong profunctors? And if you unpack this square here, oh, look, there's the other law. So we can now rephrase this definition of a locally applicable transformation. We can just rephrase it. A locally applicable transformation is a strong natural transformation between these strong profunctors. And yay, we've got a much more formal definition of what one is. Okay, so then what can we actually do with this definition now? Well, the first thing to note is that, of course, we now actually have a category. So we have a category where the objects are these strong endoprofunctors and the morphisms are the strong natural transformations between them. And we can say, well, what other structures do we have on this category? Well, it turns out there are at least 2 tensor products, 2 that I will be interested in. But one of them, it kind of takes 2 profunctors and puts them sequentially after each other. For those of you who like profunctors and know about the Cohen calculus, it's this thing. If not, you can just kind of think of, if you take the 2 profunctors and put one after the other. The other, you take two profunctors and kind of put them in parallel, and then you take a quotient, which is I will touch upon in a moment. But the idea here is we have kind of two tensor products, one that puts them after each other, one that puts them in sequence. For those who are interested about this tensor product, what's going on here is that this category of strong endoprofunctors is actually the pre-sheaf category of this optics thing that I mentioned earlier. And in fact, this tensor product is exactly day convolution over a tensor product that lives in here. But the takeaway is there are these two tensors. And we can now think, well, what happens if we apply these tensors to these objects we've been interested in for the single party supermaps so far? Well, for the one of them, we do this and we get these two, we get these spaces of maps where party A comes before party B. So A imparts signal to B, with B imparts signal to A. And with the other tensor, we get these in parallel. We get the separable maps on them up to this quotienting business, which I'm going to sweep under the rug a little bit. And now with these tensor products, what we can show is that this definition of a locally applicable transformation on the multi-partite bonds can all be kind of compressed down into this tensor product. This really does represent these morphisms. So this gives us a nice way of accessing these more general locally applicable transformations all within the same category just by this tensor. And as a good kind of sanity check, if you apply this to completely positive trace preserving maps, so quantum channels, you recover exactly the quantum supermaps in the way that normal quantum people would define them. And then we can kind of now introduce a definition using the other tensor product for these causally ordered but black box supermaps using this other sequential tensor product. And again, if you apply this to category of completely positive trace preserving channels, you recover exactly the causally ordered quantum supermap people in the quantum literature would usually talk about. Okay, so my last 5 minutes, I'll just briefly touch upon the third case. We've shown how we can recover black box supermaps that are sequentially ordered and ones that are kind of that have indefinite causal orderings to them. What's happened to the supermaps that are circuits that do actually decompose as circuits from the original category? So what's happened to the case where this actually is equal to this? Well, the first thing to note is this theorem that says that these strong endoprofunctors are the pre-sheaves of this octet place. So this means we have the Oneida embedding. We can embed all of these objects into here and get the codes that live within the same category. And what this allows us to do is to now kind of give a formal definition of what it means for a category to have a decomposition theorem for supermaps. So this maybe slightly complicated looking natural isomorphism here is literally just saying the space of supermaps is the space of cones. And you can generalize this to the n-arity case as well. And as a good sanity check, you can apply this to quantum theory, and indeed quantum theory satisfies this. And then we might wonder, well, how much more of the structure of, say, the cause construction can we get? Is this actually a star autonomous category? Do we have a model of linear logic? This sort of a thing. The answer is unfortunately no, not quite. So well, actually, both of the tensor products here are closed. And that means we can define these weak jewels by looking at kind of the internal harm into the unit object, precisely the way you might expect. And this gives us a functor, but in general, we don't find that this star is an involution. So we're not going to get a model of linear logic. We don't get a star autonomous category, but we do get a model of this sort of weaker thing, tensorial logic. And you might wonder what happens if we look at some of the objects we've been interested in so far. And one thing that's quite interesting is if you take these cones and you take the star of these, you get exactly the things that we've been studying all along here that the supermaps act on. Which then means we can restate this decomposition theorem for supermaps in terms of this star. So to have this one-arity decomposition theorem means that the Yoneda embeddings of these objects from optics actually have to be an involution. So now you really can connect the existence of this star, the existence of this thing being star autonomous with decomposition theorem for supermaps. And you can do this in the n-arity case as well. And what you see is kind of this relationship now between the star and this sequencing operator. So for those of you that know something about BV logic, you might well recognize this sort of equation. Yeah, so that's what we're asking for here, picture. Just a very couple of brief words on this. You can define a par here in the way you would expect, but it's not going to be a tensor product of this category because the star is not an involution. But it is still, you still have like strengths, and you do still get a distributor that looks a lot like the one from linear logic, but the par just isn't a tensor product anymore. All right, so what have we done here? We formalized these locally applicable transformations, uniting them with the world of the study of optics. And in doing so, introduced a framework for studying these supermaps over any symmetric monoidal category. We've extended these to include the definite and indefinite causal orderings and to connect the decomposition theorems for these supermaps with representability of these things over this category of optics. So I'll cut just a couple of thank yous to some people that were very helpful during this project. So Mario Roman, I don't know if he's actually in the room here, but many thanks to him for a lot of really useful chats. And Cole, again, I don't know, he's over there. Yeah, cheers to Cole as well for lots of chats. Are there any questions for anyone?
Are there any questions?
They are two different sets of products that same.
No, they have different internal parts. The one here was for the like horizontal line. Yeah, yeah.
What was the volume version?
What was what? Sorry, so we got this day convolution. Oh, sorry. Where do you mean? So this is a very dodgy picture. What I mean here is that so this ignore this quotient, this picture here. These things are the tensor product of the category C in prof. So these monoids of this monoid and comonoid or pseudo monoid and comonoid are these two things here, the embeddings of this tensor. So then this expression here is the bit in brackets, and then what you have to do is take some quotients of this thing because you have this strength floating around. When you do the bit inside here, what you get isn't actually a strong profunctor, or it is not the correct strong profunctor anymore. So you have to quotient some strengths, a bit like when you take the tensor product of bimodules. You have to do this like kind of, there's this quotient going on, right? That gives you the bilinear things. That's the quotient that goes on here. It's actually the same quotient that's going on here, dealt with by the coend, but in the other dimension. And the nice thing with this result from Pastro and Street is you can deal with all of that by functoriality over this category of optics instead of dealing with this quotient. But yeah, these are technicalities that we can chat about if you're interested.
Your question?
So you make very minimal assumptions.
Symmetric monoidal, yeah.
And this is like nothing apparently quantum but symmetric monoidal categories. So have you thought of this anything you can apply this to just in some other areas?
Quite possibly. I mean, I know Matt had written down some versions of like the switch or other theories. I don't know if you want to comment on that at all.
Yeah. So there's like a framework for general physical theories made up by the question you're asking. They're like school operation problems and theories. They include like classical quantum theory and stuff. And you can see that in some of those switchy things like that'll be a classical switch.
mean, yeah, just to make they show up in like sort of stuff we are doing, sort of. I mentioned like show super and that is a super magical verb.
Right.
Yeah, true.
They also come up with like. Yeah. Yes, more complex.
Could you give a bit more nutrition of the significance of the position?
Significance of them. I mean, really, it's, this is a definition here of what it would mean for a supermap and the way we've defined. If you buy our definition of what a supermap should be, which is then given by the maps here, we're literally saying these are these cones from optics. So this is by the Yoneda dilemma here, just to see that these are the holes of optics. So that really this is just that definition stated at an abstract level.
And the default here refers to.
Sorry, it's literally asking basically this, right? The point is we're asking, are these supermaps these things in our world? So if you buy our definition of what these are, you have access to these because of the Yoneda embedding, and you can ask whether they're the same. And then the thing that's kind of what was interesting about this is that you can connect it with this star operation, with the internal holes of this category, with this structure. That's what I think is interesting about it.
Okay, thank you. I don't see.
Well, like my I sent them an email from me.
Should be gives the licensation. Sorry.